You have probably seen the advice to never log secrets. Do not write passwords to log files. Do not include tokens in error messages. Do not print API keys to the console. The advice is correct, and it addresses about a third of the ways secrets end up in logs. The other 2/3 do not involve anyone making an obvious mistake. They involve infrastructure that was built to capture everything, and capturing everything is exactly what it is supposed to do. A secret in transit is not just a value moving from one place to another. It is a value passing through every system that touches the communication path, the application that sends it, the network layer that carries it, the proxy that terminates TLS and re-encrypts it, the load balancer that logs the request, the service mesh that records the trace, the observability platform that indexes the span attributes, the error reporting tool that captures the full request context when something goes wrong. Each of those systems is doing its job correctly. None of them were designed to understand that a specific field in a specific request contains a value that should never be retained. This is the transit problem with secrets. Storage gets hardened. The path the secret travels to reach its destination is almost never modeled with the same rigor. The clearest illustration of how this plays out is HTTP request logging. Most web servers and reverse proxies log incoming requests by default. The log format typically includes the method, the path, the status code, the response time, and the query string. The query string. A secret passed as a URL parameter, which happens more than anyone would like to admit, particularly in OAuth flows, webhook configurations, and legacy API integrations, is now in every access log on the path between the client and the server. Access logs are frequently forwarded to centralized log management platforms. They are retained for months or years for compliance and debugging purposes. They are accessible to every engineer who has access to the logging infrastructure, which is typically a much larger population than has access to the secrets manager. The secret was never stored insecurely. It was transmitted insecurely, and the transmission wrote it into a half-dozen secondary storage locations that nobody thought to include in the threat model. Request bodies are somewhat better because they are not typically logged by default, but error reporting tools change that calculation. When an application throws an exception and reports it to an error tracking service, the report frequently includes the full request context, headers, parameters, body, environment variables to make the error reproducible. An API key in an authorization header is now in every error report generated while that header was present. Error tracking platforms are cloud services with their own access models, their own data retention policies, and their own security perimeters. The organization that was careful about where it stored the secret has now sent it to a third party. Inter-service communication creates a different transit surface. When one service calls another inside a microservices architecture, the call typically passes through a service mesh or API gateway that records traces for observability. Distributed tracing systems capture request metadata to help engineers debug latency and errors across service boundaries. If a service passes a credential as a header or parameter in a downstream call, which is common in service-to-service authentication patterns, that credential appears in the trace. The trace is stored in the observability platform. The observability platform is typically accessible to every engineer on the team. TLS protects secrets in transit from network interception. It does not protect them from the systems that legitimately terminate and inspect that traffic. A secret transmitted over a perfectly configured TLS connection through a load balancer that logs request headers is a secret that was protected from passive interception and exposed through authorized infrastructure. The two are not contradictory. They describe different parts of the attack surface. The pattern across all of these cases is the same. A secret enters a transit path. The transit path was built for observability, for debugging, for compliance, for performance analysis. The systems on that path are doing exactly what they were designed to do. None of them knew the field they were recording was a secret. The organization that instrumented its infrastructure carefully, that built comprehensive logging, that deployed distributed tracing, that organization created more places for secrets to land than the one that logged nothing. Better observability and better secrets hygiene are not in conflict. But achieving both requires explicitly modeling the transit surface as a risk surface, identifying every system that touches a request carrying a secret, understanding what each of those systems captures and retains, and making deliberate decisions about field-level filtering, rather than assuming that the absence of obvious mistakes means the secret stayed where it was supposed to. The question is not whether your logging infrastructure is capturing secrets. In a system with comprehensive observability, it almost certainly is. The question is whether you know which ones, where they are going, and who can reach them once they get there.